Okay, we will continue from wherever we left last time. The way now my actually whole plan is I will finish up with this particular part, then I will go to what we call buffer delta. So, the problem is that there are no closed form solutions for that, but if you want to, for example, even simulate that, this is a complicated thing. So, we will try to understand that thing and how you can build up the complete simulation by actually understanding the state transition diagram of a 2x2 switch, which is going to contain one buffer per input. Okay, because so far in our switches either the buffers are only at their input or at the output. But remember, in this banyan network category, there is, if there is one path being set up, it actually blocks many other paths who are sharing the same link. Those paths cannot be, all permutations are not possible. Okay. So, the only way you can get higher throughput is because it is not a strictly non-blocking switch, it is a blocking switch technically. So, we need to put buffers. So, buffers at input and output we do understand, because it is a blocking switch. If there is, it cannot go through, just stop at the output. Now, this is different than speed up factor. Okay. And speed up is what the at one single output, if you want to pass through something, then only you require a speed up, more than one. But if the permutation is such that there is no conflict, crossbar will always permit this, but this particular switch will not permit that actually. There is a map which is possible when there is no conflict for an output port, but still you cannot set up the connection, because that permutation is not permitted. So, people thought of adding into the buffer, so we will look into that particular thing. So, that is actually from a paper. Again I will tell the title of the paper when I will come to that, and then I will probably move to voice over IP, basically SIP based system, how does it operate. So, that is a current day telephony structure. Okay. And if I am able to finish SIP before the end of semester, then we will come back to again switch architectures, and I will probably do something more on these. So, which are basically knockout switch and other kind of switches which have been proposed in the literature. Okay, none of them are actually implemented as such in hardware as of now, except this particular one, the buffer delta is technically implemented by in almost all packet switching systems. So, even if it is a IP switch, what we do is we do not actually IP switch, remember IP packets are variable length packets, and whatever we have been doing is only for fixed length frames. So, people used to call them ATM switches, but technically in the core we always built this fixed length packet switches. And if you want to implement a variable length packet switch through this, at interface board you actually splice the packets into multiple fragments, put some identifier for them for reassembly, then put the tag for each one of those fixed length fragments, and those fragments are routed to the output board. Only condition is now you require an output interface board also in the switch. You are encapsulating this fixed length packet switches, and outside input and output interface boards, these will again reassemble back the IP packet into its original size and send it forward. Usually I am looking at the switching efficiency within the given amount of hardware, how much I can pass through the output of the switch. We call it throughput, number of packets going out of the switch per unit time, per unit slot. Ideally it should be, if there are n output ports, it should be n packets per output slot I should be able to push through, but that usually cannot happen because of the statistical nature of the traffic. Okay. With buffering and something you try to improve, but still getting almost 1 is impossible. If you put a load of 1, means there is always a packet available at the input in every time slot, you will not get 1 packet per output slot coming out. Input output queuing, we have seen that particular case. For input queuing this does not happen, we actually limit to a certain value, we cannot exceed that. Okay. Well, that is again a statistical, because what will happen, once in a while you will get very large throughput and other times you get very low, but average value will be maintained at that. We always compute statistical averages. Okay. So, now let us go back to where we left. I think what I had done was, I had taken this case of the switches. There was some switch which was having some input address and which was represented by I think this is what was there. So that was the input address, and this was to go to an output address. This was B. So that was our objective. After the first switch, we know that this particular digit will be used for in the first switch for routing purpose. Okay. So before you do the shuffling, what will actually happen is I will find out the switch number. From this switch, finding out the switch number is you divide by A and take the floor function, and that will give the number. Number is 0, 1, 2, 3 and so on. So multiplied by total size here, whatever is your current switch number, because it is actually less 1 number it is if you count. So this will come out to be 0, so there is nobody. So 0 into B plus whatever is Dn minus 1. So that is what we did. So that was term known as L1. So because I am dividing by A for floor function, that is what we got. So this is nothing but the floor function part, okay, plus Dn minus 1, and this have to be multiplied by B. That was L1. This was just before the, at this point. Now you have shuffle network, shuffle interconnect basically, and this is a shuffle. So once I did A shuffling, I used the formula that what will be L1 prime. So I simply used L1 into A plus L1. This has to be, if you remember, for a Q shuffle it has to be an R. Q into R is total number of elements. So it has to be whatever is total number of elements here divided by A, because I am using A shuffle. So this A raised power n minus 1 into B. So this will be A raised power n minus 2 into B. Okay. Modulo operation. So this is what was there. In fact, what we did is we actually took this particular thing out. We wrote the whole expression. It turns out to be something like Sn minus 1 plus then everything divided by A raised power n minus 2B. What we did is in the numerator we put the all possible maximum values, and we figured out after doing all summation that that value is less than this. So this is always going to be a fraction, and when I am taking a floor function, if this is a fraction and this is the integer, this is what I will get actually. So I can replace this whole thing by Sn minus 1. Okay. So you will get, I think that is the point where we finished last time when I closed. So you will end up in L1 prime, which is given by L1 into A plus, this is the only thing which will be left here. Okay. So I think that is the point where I ended. So we have to now solve this modulo thing. So let us find out what is L1A plus S1. We expand this as an expression and we will try to understand, if I do a modulo operation, whatever is a component which is integral multiple of this factor will be removed. Okay. And whatever is left over, that will be the outcome of this modulo operation, and that whatever is left over has to be less than this value. Okay. So we will do that. So L1A plus S1, this will be now, what is your L1? L1 you have to understand is this. So I have to multiply this by A. So this will become Sn minus 1 A raised power n minus 1 I have multiplied by a already. Now S2a square plus S1. Okay. There is already a b in front of it. S1a, right. This is also fine, and ultimately this Sn minus 1 will be there. That is a term which you will get for this. Okay. You have to essentially handle this, and then by using a similarity principle and following the same thing, you come to the proof. So remember, there is one term which will go out, and this is another term which will come in. That is what is going to happen. So at the input of this second stage, I want to find out a switch is here, what happens here. That is what I am interested in actually. So every stage, what happens? This is a one state transition, or you call it at this stage what happens, and after the next interconnect, what is the number here, keep on doing it. But ultimately I am interested in their total how many, this is L1. I am interested in their total n stages, I am interested in Ln actually. Okay. So now solving this, expand. You just observe this. Okay. This will be n minus 2b. Now this particular factor is divisible by a raised power n minus 1b. So if when I will do a modulo operation, when I divide by this thing, then I will get an integer. So when I do a modulo operation, this has to be removed. So I can forget this and live with the remaining stuff. So I have done the modulo. I have to only now check if this is greater than a raised power n minus 1b. So whatever is, this can probably be written into some integer multiplied by a raised power n minus 1b plus some k. So I just want to find out that k actually. So doing that, let us find out what is the maximum value of this particular thing. Okay. So in fact still better the way I can do is, I can take this b out, because that anyway does not matter. Now the modulo of this is what will be the answer to me. So I am now going to focus only in this thing which is there in the inside brackets. Now what is the maximum value which I can achieve? So put all the maximum values of Sn, Dn, whatever it is. So we will end up in, okay, let me do it here, this side. So maximum value of Sn minus 1, Sn minus 2 and so on is a minus 1 actually. So I can put all that value. So the maximum value of this thing will be this is what will be the maximum. So I can solve it. So, total how many terms? N minus 2 terms obviously, and first term is A, so this A will cancel with this, and because I have taken B out of it, so if I multiply it by B, this will be, this whole thing now technically the maximum value will be A raised power n minus 1 B minus 1 conclusion for the, from this actually what you get is this whole thing can never be greater than A raised power n minus 1 B. So, if I take a modulo operation, I will get the same thing which is here in the argument. So, the modulo operation ultimately will give me nothing but
plus A and B.
So that's n minus 1 into n plus n minus 1.
that is a maximum value of Dn minus 1. This goes from 0 to B minus 1, Sn minus 1 also goes from 0 to A minus 1. So, I put the maximum value. I am trying to find out what maximum can be achieved by this argument.
So the middle term will also be there, plus A will also be there. In between these two values, A will also be there, coming from that numerator. The right one, sir, right? AB by B, sir, right? Next term, sir.
This one?
Next. Yeah, this one. This
हाँ
term.
तो B cancels ना. So there is a into this A raised power n minus 1
Yes, sir.
minus A B cancels, so it's a plus A minus 1 over B. So this actually cancels. Okay, so final result will be of this modulo operation obviously is nothing whatever I am writing here. That is what it will be. That will be L1 prime.
First term, sir.
First term will not, oh this won't exist, it's n minus 2. So I can keep on doing this and I can find out L2 and so on. So, but only now I think I have got the structure. So now what is L2? L2 will be nothing but L1 prime divided by A into B plus Dn minus 2. That is the operation at the second stage. I will find out which switch the input is going to by doing this floor function, dividing by A, doing the floor function. On the output side, how many was already covered by all earlier switches. In my current switch, I am going to go to this particular port number. Okay, that is the second stage. So I can write down that whole expression here, and this will turn out to be Sn minus 2. I have divided by A, so again the powers will reduce. Okay, that will be the floor function. plus sorry, there will be a b also, which will be L1 prime. You divide this whole thing by a actually. This all terms can be divided by a, this term can be divided by a, this is what will be the fraction, Sn minus 1 divided by a will be the fraction, and when you will take the floor function this will go away. Okay. So you divide everything by a and multiply it by b, and that is what actually has to come. So I can just multiply this thing by b, this can be multiplied by b, and of course this dn minus 2 will come. So remember that I am actually removing one term is being removed here, another term getting added here, that is what is happening now at every stage. So ultimately all these terms will die away with time, every stage, and only these dn minus 1 terms will come, and whatever is the output will tell what is the port number to which it is mapping. If that port number is what is being governed by dn minus 1 raised power b n minus 1 plus dn minus 2 raised power b into n minus 2 and so on till plus d0. So I am actually going to an output port address. So it gets proved actually in that process.
This will be b square. B square first term in brackets multiplied by b square.
Right, it's a b square. Agreed. This will be b square because this b has to be multiplied by that. Okay. So from here you will get a shuffle of, now number of outputs which will be shuffled are these. Earlier it was a raised power n minus 1 into b outputs. Now these many outputs will now be a shuffled. So it is a second shuffling interconnection. This will give me nothing but L2 prime. L2 prime is L2A plus L2. Now what will be the numerator? This divided by A. Q is already A, R you have to find out. So A raised power and this has to be done a modulo operation over this. So you will get L2 prime as, once you solve for this, so you have to just remember the symmetry now. The structure of the earlier expression, this actually comes from there. So L2 prime is one term has actually again gone from here, n minus 2, Sn minus 2 has gone now, it is no more there, plus so you multiplied that whole term by A. So it's a modulo operation has to be taken. So we now know which terms will go away during modulo operations or during floor functions. Okay. So yeah, L2A will give this. Dn minus 1 b plus dn minus 2b into A. This will come from your floor function. Okay, this will come from your floor function. Earlier it was Sn minus 1, this time it has to be Sn minus 2. You take the floor function of that, you divide that whole thing by a raised power n minus 3 into b square. So this term will be completely deleted. Rest everything you take care, and you will find out that does not, that is a fraction, that is less than 1. So that can be removed. So Sn minus 2 will be the only one which is left out on that side. So from here, so you can now just use those clues. Okay. Or if you want, you can actually put the actual values, compute the series and figure out, yes, it will be always less than 1. And then of course from here, once you know this L2 prime, you can find out what is L3. L2 prime divided by A into B plus dn minus 3. You divide this whole thing again by A, which can be done, all these will reduce by that value. This can be divided by A, this will be lost because when I am taking this floor function, okay, and plus dn minus 3. So what you will get, you can actually directly get the clue, Sn minus 3 you will multiply it by B, so it will be B cube. This thing will be divided by A. So these are being wholly divided by A, so does not matter. Last one will not remain there, and then I multiplied by B, so I will get this value plus dn minus 3. Very similar to that this expression. You can see every time I am adding now, I am forming a series at every step. Okay. So I think so far we do understand how it is happening. So by intuition you know that it is going to work, but formally if you know I, you have to prove for I plus 1, and henceforth you will say because it was working for 0, it is working for 1, it is working for 2, and it works for, if it works for I, it works for I plus 1. So it works for everything, for all integers. So what is it for n, and get the estimate, and that is what has to be done. So at Li is the line number just before the stage I, okay. So that Li is
after stage I, because L1 we are doing after first stage and before first A shuffle.
right, after stage I, agreed, it has to be after stage I. So look at the similarity of whatever was the earlier expression, from there it comes. This is what will be there after the stage I. So from there you can actually find out what will happen after stage shuffle interconnection, and then what happens after stage I plus 1. Okay. Again following the same principle, first of all you have to do the shuffling. So shuffling again says it has to be Li, whatever shuffling you are doing plus Li divided by whatever are the number of lines in that which are being shuffled. This will be a raised power n minus I plus b raised power I think that is what it will be.
Minus 1. A raised by n
I minus 1,
plus
right. I hope it is right here. No.
N A raised power of n minus I minus 1, sir. A raised power.
B raised power I. Total sum of these two is always n.
Yes, sir. So this is the total objects, and this we divided by A. So this will be A raised power of n.
That is for R actually, when
Yes,
I am
sir.
taking
Yes,
in the
sir.
base.
So this will be n minus 1, I minus 1. Bi. Yes.
This is I think what it should be. So for I plus 1 I can now find out what is Li prime, and from there I can get Li plus 1, because that is a step which is required for induction. So, this will give me nothing but Li prime. So, I can just multiply this thing and I will get so it is b raised to power I. Okay, plus I have to find out this operation. So, you divide this whole thing same Li by a raised to power n minus I minus 1 by bi. Only this thing will be the whole thing which will be available, rest everything will become a fraction. So, what you will get is s of n minus I. Now, when you take a modulo operation, only this a raised to power n minus I into bi is complete, rest everything will still remain a fraction. So, what I will get is L1 Li plus 1, yeah, first of all Li prime only, I have to solve this because Li prime will come after modulo operation. So, I have to do a modulo on this. So, once I do a modulo, so Sn minus I1 will actually go away, rest everything I have to write. So, this one will be yeah. Right, these things will also come as it is intact. This what will be Li1 prime. So, Li plus 1, you can again use same formula, you divide by a, take the floor function plus whatever is the next digit, which is d raised to power n minus I minus 1 now. Okay. So, n minus whole bracket of I minus 1, that is what it will be. So, when you divide this whole thing by a, so what goes out? Yeah, this thing is wholly divisible, this thing is wholly divisible Sn minus I, which what comes out. Okay, Sn minus I divided by a will be the fraction, so that has to be removed, rest everything will be there. So, it will be Sn minus I minus 1 because everything has to be multiplied by b to get Li plus 1. And of course, the last one. So, I think this fits. If it is for I, it is for I plus 1 is proven. So, now I can go and estimate for I plus Ln after nth stage. Sorry, I am using I think a small n everywhere. So, what will be Ln? I can just use this expression So when I reaches to n, all these terms will actually go away. This for I plus 1, remember. So n minus I plus 1. So when I am looking at n, so s minus n minus n, that will be s0 a raised power something, and that is how it should actually come. In fact, that term will not be there. No, that cannot be b. This is the actually from at this stage, after that there is an interconnect, and after that I am doing a switching operation. So which is the digit which is used there for routing purpose? That is that one, n minus I. In fact, you should always write this thing this way for clarity. This particular digit is used for routing there actually. So all these terms will be actually almost gone by the time you come to n, and you will end up in getting dn minus 1 b raised power n minus 1 because I plus first stage it was b raised power I. So nth stage it will be n minus 1 and so on. And this is nothing but the output port address. So a shuffle net interconnection actually is a delta routing network, delta interconnected network. Of course, if there is a confusion, you always try to find out what will happen for n minus 1 stage. Find out what is going to be ln minus, not ln but ln minus 1. So from here you should be able to get, there will be only one term left which will be done away with in the next step, and you will end up always in the routing at the destination output port address. Okay. So that was the example that shufflenet, yes, does work like a delta routed network. But so far you follow the principle, you can always create anything. Interconnection is your choice. How this kind of switch will be implemented? So if it is a 2 by 2 switch, it is very simple. You look at the inputs which are coming in, there are only 2 inputs, and they will have a bit which is deciding bit actually. So there has to be always a controller sitting in. In fact, I can make a parallel interconnect and also keep on sending the control bits one by one separately as a parallel line, or it can be attached as a tag in front of the packet. If it is attached as a something in front of packet, you require interface processor. It receives the whole packet, gets the tags out. These tags are being sent to the controller. Okay. So dx dy. Interface board has been designed to take specific bit out of the tag depending on in which stage you are putting in. This can only keep an action of whether it is in cross or bar state. If it is in cross state, the mapping is this, bar is, cross is this and bar is this. So that control has to be exerted. That is it, nothing else has to be done. So if there is a conflict, both of them want to go to the upper port or both of them want to go to lower port, you just randomly pick one and forget about the other. Okay. This is inefficient in that sense actually.
So how to do delta and cross once again, sir? Delta and cross, parallel, straight and cross.
If this is x and x prime connection, that is a bar. A cross actually means your this input is now connected to this input is connected to this, that is a cross state. You can actually in electronics, it is pretty simple, you just can build up a AND gate and put it there, that is acting as a switch, but it is a non-relational switch actually, because the AND gate switching, how fast AND gate can change state from 1 to 0, it basically will decide, because what is happening is logically in AND gate only one input you are using as control, other one is this, but this is actually changing every time it goes from 0 to 1. This transition bandwidth is decided by this gate itself, gate design, it is not a relational switch. We call it a non-relational switch, there is no relation, it is all governed by the hardware, how fast you can, what is the bit rate which can be put in. Okay. There is another kind which is, one example is optical coupler. So if you use for example a optical coupler, typically these are built over electro-optic materials, and if you apply electric field, so if you do not apply electric field, this may be in bar state, when you apply electric field you change delta beta, beta 1 and beta 2 are basically difference of propagation constant of two modes. Two eigenmodes in this coupled system is actually are like this, one is this, one is this. So one is with beta 1, other one is beta 2, and the difference between them is known as delta beta, that is known as delta beta coupler actually. This delta beta can be changed by applying electric field. So usually when you put a profile here, this will excite, this is not the mode of this system, these are the only two modes. So this has to be now represented by uniquely by a linear combination of these two modes. If these are both of equal strength and you add them, you just make a 180 degree phase shift for this one. So these and these will become in phase component, okay. And currently what is there out of phase, this is going to be there. If you make it 180 degree phase shift, these two will be cancelling each other and these two will be adding. So these two modes will be excited with equal strength actually. And as you propagate, and if you ensure this length is sufficient enough so that you will have a pi phase shift, what will find out, these two will come in phase and these two will go out of phase at the output. So whatever power you are inserting here will come out at this port, that is a cross state. If you change your voltage or delta beta into length, it becomes 2 pi or integral multiple of 2 pi, power will remain in the same fiber. But one of the important thing, when I am going to cross to bar state, that will take say a few milliseconds. But this time taken to go from cross to bar state does not decide what will be the bit rate which can be injected into the system, because this is not changing the state of system. So this is transparent to input to output. This is a relational system. In case of a gate, this is not a relational system. Input and output are not at all related bit rates. The system actually tells what is the maximum bit rate which can be there. So that is also another one kind of configuration which can be there. But scheme usually will be very similar to this. And if you have a kind of not a two, because in this case logic is very simple, if both are same, choose one of them randomly, other one you simply drop. But where you will drop, what does that drop means? So if it is a gate based implementation, only one path, because what will happen is you will have, going from here you will have a gate, going from here also you will have a gate with the OR option here. Similarly from here there is going to be one gate, something like this. If you put a NOT, then there is a problem actually, because both of them cannot be switched off simultaneously. Sometimes both of them might have to be switched off if there is a contention, because you are dropping that packet, so that packet will be lost. So it has to be received, analyzed and then retransmitted again by this interface board. You have to repeat it multiple times in the switch. It is not that it is not like a crossbar where only interface board does the analysis, then internal just set the cross points, things passes through. No, you require basically all clock recovery, putting into memory, analyzing everything at this point. and every 2 by 2 cross point requires this. So, amount of hardware required is higher actually compared to a simple crossbar. That is a penalty which you pay for tag switching. So, every 2 by 2 cross point require a processor, however small it is, but it requires a processor. Crossbar, one processor is good enough, and every interface board there has to be a processor. So, technically here number of interface boards which you require are, one is the main interface board in the beginning where the tags are inserted, and if it is IP packet variable length switching, it also does a splicing into constant fixed length frames. Output side, it will be spliced back, joined together, the splitted stuff to make the again variable length IP packet. These are two special kind of interface board, then every stage will require interface boards at the input side. Well, that is a complication here. Okay. And this is, I think, is a problem, but with the good, now in VLSI it is technically possible to implement all these details. So, this has actually taken off as such. Now, can we improve this further?
Sir, we are implementing 2 by 2 by gates using VLSI, sir. That is, now this
The whole matrix itself is built in VLSI now.
But that will not have a processor if you built in VLSI.
No, you can build the processor also. Just repeat the same thing, same design multiple times,
so now
and connect them with the buses.
Now we are done away with crossbar now, sir. Now that it is implemented in.
Packet switches are all implemented this way. No crossbars. Crossbars actually are no more used. In fact, for even speech signaling, we do not require crossbars anymore, because speech is now communicated over a packet switching system. So, underlying switch still remains, this is transparent to your voice transport system. Earlier voice transport system was knowing that there is a switch beneath. You are setting up paths. Now, for you, setting up path actually means you are bus simply forming a packet and putting something in the header. That is the switching functionality as far as the voice transport is concerned. So, hardware takes care of that. Now, how to improve the functionality? I have to introduce buffering. Okay. So, buffering means if this is there, I am going to have one buffer. Okay. Now, if there are two packets coming, two packets come into the system, then what will happen? There is a contention. One of them can go out directly, other one can be buffered actually. Now, here slightly a different thing, because I am now introducing for the first time the feedback system. Okay. So, there is a feedback loop which is there, so there is nothing actually gets lost. You only transfer the packet to next stage if you have got a buffer available, otherwise you do not do this actually, it is as simple as that. Okay. So, do we put an output buffer or an input buffer? The question is this: if I want to build up a buffer, I am going to still build the same delta network, but now every intermediate switch will have a buffer. Now, if I make this as an output buffer, I am connecting to some other switch. Now, look at a situation when the buffer is not here, but buffer is here, and they are on the same chip or a same substrate or same board. So, distances are very small, I can build up backward communication also. So, whether you put the buffers here or whether you put the buffers here are actually same, it does not matter. Now, question is how to analyze the performance. Now, there is one way is to actually build up a simulator with this, but doing simulation you have to now build up a model of this system, of every switch, how this is going to operate. So, the model which we are going to look is basically based on a mechanism called feedback. So, if this buffer is there, if this buffer is free, I can send the information back, and this can maintain a state whether buffer is available here or not here. Okay. Based on that, whatever is occupied in this buffer can move or cannot move. So there, for example, there can be at the input the packet for the same output. If this buffer is going to be free, then only this flag will say the buffer is free, and both of them will be told, one of them will be picked and will be pushed into this buffer, other one will still remain. Now the packet from the previous stage can only come when this buffer will get free. So it's like packets are hopping from one buffer to another buffer, and if the buffer, if the packet in front of you actually moves ahead, then only you get the chance, otherwise you just remain there. Under this situation, under given load, what is going to be throughput performance? That's basically is the issue. At some point of time you will find out you cannot achieve higher throughput. Throughput is limited, it cannot be unity here obviously, because there are contentions. Okay. So what I will do is, actually I am now ending here, because I think I will cover up this thing. I am not taking 2 hour class today, honestly speaking, only taking 1 hour. I will take up another Saturday sometime and then actually take 1 hour extra there. So the paper which you have to follow for this one, I am just giving so that you guys actually can go back and read it before you come to the class, because this is slightly tricky part, especially state transitions and how to change the matrices and how to compute. Simulator is not given code here, but once you understand this, then you can write a simulator. So doing simulation is not a trivial exercise, you have to build up a complete mathematical model. So this paper, actually large part of it is actually on how to build up a model of a switch so that it can be simulated, and you will be using a Petri-net model for this actually. So Petri-nets is what I taught in the previous semester, same thing will be used here again. So this one is dice and jump. This is IEEE transactions on computers actually. I like this one because it actually tells for the first time the complete details before you start doing the simulation part, and theoretically also an analysis actually can be built for this, that's one good thing. Title is Analysis and Simulation of Buffer Delta Networks, and Simulation of Buffered Delta Networks.
So basically we are doing input queuing with the output with the
But now in
flag
every node.
and with the flag at the output, which corresponds to the input of the.
So you can move ahead only if the queue is in front of you is empty, otherwise you remain in blocked state. So input also cannot come. See, even if a packet arrives at the input, but it cannot enter because somebody else is already occupying your state. I am not dropping the packets in intermediate switches, remember, I am not dropping the packets here. Now that is a different case again.
But if you use output queuing, you will have to drop packets at a particular switch. If you use output buffering.
How I will do? There is nothing like output and input. What is the output of a switch is the input for the next stage. So model is same, you take either input or output. So this is actually input, queue is being considered for every switch. A packet comes in, only one packet can be buffered here, and the packets from these buffers will move to further stage. If for example this buffer and this buffer both are free, both flags will show, and this packet has to go here, this has to go here, they will go immediately. Okay. If both have to go here, only one go and one will remain blocked. If both have to come here, one will go and one will remain blocked. Based on that, this signal will go back. So, continuously state signals are moving in backward direction, packets are moving in the forward direction. So, it requires exactly n steps to move to n stages out of the switch. So, there are sub steps which are being defined for movement. And after this, I think we will then go to VoIP or SIP based systems actually.